So I'm almost done with the solutions. They should be up this afternoon for the exam. Okay, so the exam solutions should be up this afternoon. And we hope to have them graded by Monday of next week. What I was going to do today was continue our discussion of correlated data and specifically talk more through the core script.r file that I put up and introduced last week. So the idea of this script, it's a long one. We won't go through all of it this semester, but it has simulations in it that illustrate the impacts of correlation. I said last time that correlation is important, and if we don't account for it, it can impact our inference. The way that it impacts the inference depends on the nature of the correlation. I'll show you that today. If there's correlation, if there's positive correlation within a comparison group, like if you have a treatment versus control trial, and there's positive correlation within the treatment group and positive correlation within the control group, then the impact of that correlation is to decrease power, decrease statistical power. When you have positive correlation within a comparison group, it's like you don't have independent realizations from the population. It's like you have a smaller sample size. But in that same scenario, treatment versus control, if you can engineer it so that there's positive correlation between the groups, such as with a paired design, then we'll see it actually increases power. So correlation can be good, as long as it just depends on how the study is designed. But either way, you want to account for it. If you don't account for it, then your results can be misleading. So I did this on Friday. Let me redo it. I'm going to simulate a so-called one-class case. So not treatment and control, but just a single population that we want to estimate a mean for. Yes? It is. So the question was about, when I say increased power, does that have to do with the variance? The impacts of correlation are seen in variances, standard deviations or standard errors. When there's positive correlation within comparison groups, then the usual IID-based variances that you compute are wrong. They're too small. The variances are actually bigger than you think they are. Whereas if there's correlation between the groups, the IID-based variances are bigger than they could be. So one way to affect power, the probability that you correctly reject the null hypothesis, is to increase sample size or decrease variability. And correlation can affect or does affect variability. But the way that it affects it depends on the design of the study. It can increase the variability or it can decrease it, depending on how it comes in. So we're going to simulate a data set like the one described in the notes. So we looked at one example scenario in which there was correlation. A simple scenario, a single population, a one-class case. There's one mean that we want to estimate, mu, and there's a common variance. Every individual draw has a common variance, but every pair is correlated with correlation rho. So the matrix of variances and covariances looks like this capital sigma here. back to the script, we're going to simulate from that scenario. Our n is 100. Our mean is 5. Our standard deviation is 1.5. And the common pairwise correlation is 0.95. We could fiddle with these numbers and rerun the simulation to see the effects of changing those parameters. But for these, let's generate some data. So what I'm going to do is use the multivariate normal random number generator. Right here. This is give me random draws from a multivariate normal with a mean equal to mu, a vector mu, and a covariance matrix equal to what we said it should be in the notes. So let me run the first part of this, and we'll take a look at capital sigma for a second. So capital sigma is an n by n covariance matrix. I'll show you the first 5 rows and first 5 columns. So the diagonal, that 2.25 all along the diagonal, that's sigma squared. That's the variance of each of our realizations. In the off diagonal is 2.1375, and that should be the covariance between any two pairs. The correlation between any two pairs is rho, and then the covariance we've seen in the notes is the correlation is covariance divided by the product of the standard deviations. So that means the covariance is correlation times the product of the standard deviations. So if I do correlation times the product of these, that should just be sig. So times the product of the two standard deviations gives me that 2.1375. 100 by 100 matrix containing variances and covariances. We're actually going to simulate 2 data sets. One is where there is no correlation, in which case our data are just IID normal. And Y underscore core for the actual correlated data case. So to generate correlated data, I'm going to use the multivariate normal. Multivariate normal is for vectors that are jointly normal. After I do this, we have a bunch of data. Y independent and Y core, 100 by 500, and the reason there's 500 columns is because each column represents a simulated data set. So we're going to play around with what happens when you have a sample of size 100 with these parameters, when they're independent and when they're correlated. I did 500 simulations so that we can investigate operating characteristics. Simulations are good for repeatedly generate data, apply some technique to it, and then look at the average behavior over the simulations to learn about, for example, power. Okay. These plots are informative. What I'm going to show is what are called index plots. An index plot, if you have a sample of size 100, then an index plot is put 1, 2, 3, ... 100 on the x-axis, and the y value is the observed value for each of the 100 individuals. Here is an example. Let me change this to the first. There's no reason to start with the third one. So I'm going to show for the very first simulation, the first out of 500, what these index plots look like. So we saw this picture last time. 1 to 100 on the x-axis, and then the dots and being connected by different line segments are the actual observed data. The blue is the independent case, and the red is the correlated case. So what you can see is that blue has more variability than red. In fact, the variability of blue is this 2.25 variance. But the red, the variability within this sample is much smaller than this 2.25. That's because of the strong positive correlation. And remember, if we rerun this, we'll see different pictures. So let me just regenerate this a few times. Here's a new batch of simulated data. Move this over. Look like this time. Blue is qualitatively indistinguishable from the previous simulation. Red, again, has low variability, and in this case, it's centered away from the population mean. Population mean is 5. That's where this horizontal dashed line is situated. When we have such strongly correlated data, it's like we don't really have 100 independent draws from this population. It's closer to the case that we took one draw and then a bunch of correlated observations around that one draw. The red does not vary as much as the blue does. The red is constrained to stay very close to its original value. So if we did a study and collected 100 individuals, this could be our scenario. If we didn't account for the correlation, we could be looking at a spreadsheet with the red dots in it, with the red values in it. And if we treated that like an IID sample from this population and took maybe a sample mean to estimate the population mean, it would be biased. It would be wrong. The sample mean of the red is like 4.5 when the population mean is like 5. On repeated sampling, if we got another sample of 100 and did this again, we would see the red, again, not varying much, but the starting point changed. It randomly changed to be a little above 5 this time. And on repeated sampling, if we did this many, many times, on average, the red X bar will be unbiased. For every time it's biased high like this, it'll be biased low of a similar magnitude. The problem is that for any one sample, we have potentially big bias. Okay. Now look how this translates to sample means. If we wanted to do inference on the population mean, we would use a sample mean as the estimate. So let's take all of our 500 simulated data sets and compute y bar for each one. I'm going to have 500 y bars under the independent case and 500 y bars under the correlated data case. What we expect for a sample mean, if we have IID data, say y1 through yn, IID from some population with mean mu and variance sigma squared, y bar is the sample average, I equal 1 to 100, n y I. And our usual results about the sample mean are that, number one, it's unbiased. Its average value is equal to the population value. That means if you repeatedly sampled from this population and computed y bar every time, on average, those y bars will equal mu. The other thing that we expect for a sample mean has to do with its variance, namely that the variance of y bar is equal to population variance divided by sample size. Now let's go look at our simulated data and see how we match up or don't match up under the two scenarios. Here are 500 y bars for independent case and correlated data case. I'm going to draw histograms of both of them. These histograms are pictures of the sampling distribution of y bar. I overlaid them on top of each other, and what we have is the red, the blue being the independent case. So that tight blue histogram centered at 5 is the sampling distribution of y bar when n is 100 under this scenario with independence. The variability is not sigma squared. The variability of y bar is sigma squared divided by the sample size. The variability of a sample mean is inversely related to the sample size. The fact that we had a sample of size 100 allows us to have a pretty confident region about where the mean is, the population mean. But the sample means under the correlated data case are much more variable. That red or pink histogram goes well beyond the limits of the blue one. So what that's illustrating is that y bar under correlation is inflated. The variability of y bar is inflated. It's not sigma squared over n anymore. If I go back to the notes briefly, mentioned here, I said y bar, what do we know about it? Even with correlation, its expected value is mu. Good news. That means I don't have to worry about how to estimate the mean. I can just use a sample mean. It's the variance where the problem is. So we figured out what the variance of y bar is under the generic correlated data case. And it ends up this way. So this result is sigma squared over n, but there's some extra stuff. If rho is 0 and we have IID data, then we have our familiar result about the variance of y bar, sigma squared over n. On the other extreme, if rho is equal to 1, then the variability of y bar is just equal to the population variability. So the reason for that, let me remake one of these pictures up here. The reason for that has to do with the low within sample variability in this correlated data case. it's almost like with such high correlation, it's almost like you don't have a sample of size 100, you have a sample closer to size 1. It's like you took one draw, that one draw in this case from the distribution with mean 5 happened to be up here. And then everything else tracks that really closely because of the correlation. So y bar here is going to be far from 5. But like I said, for every time the correlated data is situated high, it'll be situated low with a similar magnitude. On average, y bar will equal 5, but the y bars are more variable because of the correlation. And that translates to problems with the sampling distributions. If I did a regular t-test or t-based confidence interval, when I had correlated data like this, it would be wrong. The standard deviations would be too small. We would have anti-conservative inference. I say it's a 95% confidence interval, but it may only be a 60% confidence interval. So the next batch here in the script investigates confidence intervals. Let's see how this translates to impacts on our inference. So what I'm doing is for each of the 500 simulated data sets, I am computing 95% or nominal 95% confidence intervals. What it's doing is, how do you usually compute a confidence interval for a mean? A 95% confidence interval for a mean would be estimate the mean and then go plus or minus some cutoff or critical value. In the normal case, the number we would use is approximately 2, or exactly 1.96, times the estimated standard deviation of y bar. So back in the script, I'm going to do that for all 500 simulations in the independence case and in the correlated data case. If these are real 95% confidence intervals, then 95% of them should contain the truth. But we're going to see that since the standard deviations are wrong, the coverage will be lower than 95%. Let's do this first. Coverage of our confidence interval in the independent case should be 95%. 95% of those simulated data sets, when you went in and created a 95% confidence interval, 95% of them, or 96%, close enough, contained mu equal 5. But when there's that strong within-class correlation, positive within-class correlation, the intervals were terrible. Only 5% of them contained the truth. So in this case, you have a spreadsheet with 100 rows in it. You treat it as if it's usual random sample IID data, use a T or Z-based confidence interval, and it would be incorrect. You would not have the correct interpretation. So again, that's why as an analyst, a data analyst, you want to ask the questions, how did these data get produced? Thinking in terms of, is there a possibility of there being correlation somewhere in here? Here is a plot showing each of the intervals, like this. Blue is the independent case, red is the correlated data case. The true mean is at 5 on the horizontal axis. So there's a dashed line segment running vertically at mu equal 5. All those little blue line segments represent 95% confidence intervals. There's 500 of them because we simulated 500 data sets. So 96% of those blue confidence intervals contain the truth. We expect 95%, so the 96 is just due to random variation. And the red ones are what we would have called 95% confidence intervals for mu, but you can see that they tend to be very far away. Their lengths are much smaller than they should be. We are underestimating the variability. And so almost all of them do not contain mu equal 5. The next batch of code repeats the above simulation, but it does it in the two-class case, say treatment versus control. Let's do inference on a mean difference, the mean in treatment to the mean under control. And the way I'm going to simulate this time is like the above case, namely positive within class correlation. So I'm going to simulate data such that there is, I'm going to do it to a tune of rho equal 0.5 pairwise correlation in the treatment group and rho 0.5 pairwise correlation in the control group. There's no correlation between, but there is correlation within. And we have similar impacts. I'm just going to quickly run this to look at sampling distribution of mean differences. You don't have to follow through all the code in this script. So this is the analogous picture from that one class problem to the two class problem. I simulated data so that the mean difference was 1. Treatment minus control on average equals 1. So the middle of this distribution is at 1. And blue is for independent, red is for correlated. So it's the same thing. The story is, or part of our story is, if there's positive within class correlation, then your standard errors are bigger than you think they are. And if you don't do something to accommodate that, you will get anti-conservative inference. You say it's a 95% confidence interval, but it may in reality only be a 50% or even a 5% confidence interval like we saw in the previous simulation. Now let's look at what happens when we have positive between class correlation. Simplest design where you would see this is a paired design. We're doing an investigation of a cream to, or let's say some treatment to whiten your teeth versus a control. And so for every person in the study, we randomly pick your top teeth or your lower teeth to put the treatment on, and the other one gets the control. Every person gets both treatment and control, in which case there's positive correlation between my top teeth under this condition and my bottom teeth under that condition. Paired data. So again, let's consider sample sizes of 100. Let's do 500 simulations. The mean is equal to 5. I'm going to allow for the mean difference between treatment and control to be equal to 1. Standard deviation 1.5 and moderate positive correlation. That correlation only applies within pairs. That's the only place there's correlation in this simulation. So I'm just going to run the data. Some of this is more than we need, so I'm just going to skip to the punchline. Let's do this one. Okay, so this is a simulation-based power curve. Delta on the horizontal axis is the mean difference between treatment and control. When delta is equal to 0, there is no difference between treatment and control. or in other words, the null hypothesis is true. And so the power, quote power, is really something we might call type 1 error rate. And here it is correctly at about 0.05 in every case, so that's good. The distinction comes, the difference between these curves comes as delta gets bigger, and namely, or in particular, the correlated data analysis, an analysis that accounts for the correlation, and I have two of them here, the red and the green dashed curves, have greater power than like a two-sample t-test. So for these data, you could throw them into a two-sample t-test, even though they're paired. That does not bias your results, but it does decrease your power. When you have paired data, you have greater power when you do a paired analysis. I have two different correlated data analyses represented here. One of them you already know, it's just the paired t-test. Paired t-test, you take my top teeth minus my lower teeth, and then you do a one-sample t-test on those paired differences. That's a simple way to appropriately account for correlation. A more sophisticated way we're going to learn, and the red curve is for that more sophisticated way. Basically, we're going to learn how to do regression with correlated residuals. The blue curve, again, is just like a two-sample t-test, totally ignoring the fact that there's pairing. So, correlation is important. It makes a difference. It impacts your inference. The way that it impacts your inference depends on the nature of the correlation. With positive within-class correlation, it decreases power. It can result in anti-conservative inference. When there's positive between-class correlation, incorrectly analyzing the data by not accounting for the correlation decreases power. So if you have, a fixed budget and you're trying to design an experiment with best, chances of yielding positive results or positive findings, if you can engineer the data to have positive between comparison group correlation, you're making better use of your money. You get more bang for the buck when comparing groups, if you can make it so there's correlation between the groups. Okay, that's as far as I'm going to go in this script for now. I've got more stuff in here that we'll revisit. Let's go a little further in our notes now. Okay. So a little bit of a change in gears. I want to define some things. Want to be able to talk in terms of clustered data. There's multiple ways to represent correlated data. There's the time course kind of thing. There's spatial. A general way of representing correlated data is as hierarchical data, in the sense that data are collected from specific levels within a study. So, for example, in a medical setting, we might have, this is one actual study, where there were 44 doctors, and each doctor was assigned to a particular level or group. Is your practice about treating back pain? Do you specialize in low treatment effect conditions, or moderate or high? Actually, these are medications. So do you use little medication, moderate medication, or high medication? Or just bed rest? For each physician type, we have some number of patients. Each physician gets some number of patients. but the physicians themselves are organized into these little groups. And then each patient is followed and measured multiple times. 1 month after the start of the study, 1 year, and then 2 years. So, in terms of statistical lingo, these are hierarchical data. The data are collected within like categories that have common characteristics. So common characteristics within levels of a category is one way to generate correlated data. Observations within the same level are more similar to each other than to those in other levels. So the patients who are being treated by doctors who tend to prescribe high doses of medication will be more similar than patients who are told to just have bed rest. Okay, this is a mathematical representation of the two-class problem where there is positive within-class correlation. I'm not going to go through this in detail, but this basically summarizes one of those simulations that we did, the second one that we did, where we had two classes, treatment and control, and there was positive within-class correlation. Let me just illustrate how we can go from this kind of scenario to a regression model, because we want to keep getting back to regression models. Very useful representation of data. These data, two-class with positive within-class correlation, can be represented as y equal design matrix times a vector of coefficients, where the design matrix has ones in the first column to pick up the intercept, and then the second column is either 0 or 1, a bunch of zeros and ones. 0 could be for control, 1 could be for treatment. This would essentially look like this model. Yi is beta 0 plus beta 1 xi, where xi is equal to 0 if individual I in control group, and 1 if individual I is in treated group. And we saw in our first regression notes that this is a bona fide regression model. Even though x is not numeric, it is a valid model representation. And inference on beta 1 is inference on the mean difference between treatment and control. Essentially, beta 1, inference on beta 1 is equivalent to a two-sample t-test. So I can represent this kind of data as a regression model. What has happened is that those epsilons, the residuals, are no longer IID. The residuals now have to, my model for them has to reflect the correlation that we think is there. I wrote the entire covariance matrix of epsilon this way. It is called block diagonal because with the first half of the data being control and the second half being treatment, there is within class correlation. So within the first half of the data, those are all individuals from the control group, we have correlation. And assuming the same kind of correlation for the treatment group, we have the same capital sigma for the latter half. The off-diagonal chunk is correlation between classes, and we don't have any, so it's 0. But long story short, we can take correlated data, express it as a regression model, And now that we have correlated data, we need to think about how to accommodate this guy, because it's no longer IID errors with a common little sigma squared that applies to everybody and zero correlation. So generally, now that we're working with correlated data, we're going to say, let's consider a regression model, y equal x beta plus epsilon. And epsilon now is not IID. Still has a mean of 0, but now the epsilons have potentially arbitrary correlation inside of them, represented by capital sigma. We saw earlier in these slides that beta hat, the usual beta hat, IID-based beta hat, x transpose x inverse x transpose y, that's still unbiased. Expected values are not affected by correlation. It's the variances and standard deviations that are. So we could, with correlated data, get unbiased estimates of the regression coefficients by just doing usual IID regression, like LM in R. Suppose that we know the nature of the correlation. We know like which individuals, which observations are correlated with each other. And we say something about the nature of that correlation. For example, in the paired case, suppose we had n is equal to 100, and the first 50 are treatment observations, the last 50 are control observations. And suppose that like individual 1 and individual 51 are the same. It's treatment measurement on the first person, and then control measurement on the first person. So the pairing goes like 1 and 51, 2 and 52, 3 and 53, and so on. Under that scenario, we can write the structure of the covariance matrix. We know what it should be. Assuming common variance, every pair can be assumed to have a correlation. Let me draw this briefly. Paired case. Let's say we have y1, y2, yn over 2. Let's say these are the treated group, and then yn over 2 plus 1, and yn over 2 plus 2, ... yn are the control group. And this is the same individual, that's the same individual, and that's the same individual. Paired data. Every individual measured both treatment and control. Then under this scenario, these are independent of one another, and those are independent of one another. It's the between class comparison where there's actual correlation. So if we think about an n by n covariance matrix, we can partition this thing into different pieces. Let's call first, there's a sigma 1, 1. This would be n over 2 by n over 2. Covariance matrix for the treatment individuals. Then there's a covariance matrix for the control individuals. Call it sigma 2, 2. And there's an n over 2 by n over 2 matrix of covariances between the treatment and the control individuals. we have that sigma 1, 1, because the treatment individuals are a random sample, this would just be little sigma squared times identity, like we did with usual regression. Similarly, sigma 2, 2 is sigma squared times I. But sigma 1, 2, in IID regression, sigma I2 would be 0, all zeros. But we have pairing. So we can write it like this. Down the diagonal of sigma 1, 2, first row, first column of sigma 1, 2 is covariance between individual 1 treatment and individual 1 control. So we need a rho times sigma squared there. Down the diagonal represents all the pairs. Off diagonals represent like individual 1 treatment with individual 2 control, and there's no correlation there. The only correlation is within the pairs. So the reason I wrote it that way is because now we can say I have an expected structure. If I have paired data, I expect the covariance matrix to look like this. I don't know what sigma squared is, and I don't know what rho is. But that's okay because we can estimate them. In IID regression, we had to estimate sigma squared anyway. Remember, we estimated as basically a variance of the residuals. So we can do that again. And we'll see, we can also estimate rho. Just take all the pairs, and you could estimate a correlation coefficient. So if you have estimates of sigma squared and rho, then you can use them to get better estimates of beta hat. Or if you went ahead and used the IID regression model, we can use them to get correct standard errors. So namely, if you did this, IID regression, the variance of beta hat under that scenario is this sandwich-looking thing. X transpose X inverse X transpose, sigma in the middle, and then the transpose of the left part on the right part, X transpose X inverse. And then if we can estimate sigma squared and rho, then we have an estimate of sigma. I can put a sigma hat in here. And at the end of this, we would have standard deviations of the beta coefficients that we could use to get valid inference, p-values and confidence intervals. Long story short, we're starting to learn how to do regression when there's correlation in the data. We can get unbiased estimates of regression coefficients and correct standard deviations so that we can get correct p-values and confidence intervals, even when there's correlated data. Okay, we're out of time. Let me show you where we're going. The main thing I'm going to focus on for us, we'll spend a fair amount of time here. There's two methods that are commonly used to do regression with correlated data. One is called generalized estimating equations. That's a marginal analysis. I'll tell you more about what I mean by that. And the other is random effects models. Those are called conditional models. Both of them are valid. They're slightly different interpretations of the results. I will prefer GEE for reasons that we'll discuss. Okay? Piece of cake, right? Questions? Okay. See you Wednesday.